Welcome again. Hello everyone. In continuation of this chapter, heat exchanger, we are going to understand the next topic, which is known as fouling factor, and it is represented by capital R with subscript F. It is a very important factor when we are studying the heat exchanger. We can say after certain period of operation of heat exchanger, its surface which is in contact with the fluid, let's say it is a pipe, the surface which is in contact with the fluid is subjected to deposition of fluid impurities, sort of scaling. We can say there is a formation of rust formation and other reactions between the fluid and the surface. To consider this effect, we can say this effect is approximated by introducing one more thermal resistance. It is considered by considering one more thermal resistance, and that thermal resistance is known as fouling factor. Its value depend upon various parameters. The main parameter is operating temperature and fluid velocity. The reasons fouling may be of two reasons. We can say fouling of a heat exchanger, which is a sort of scale formation or a rust formation due to impurities. It is due to two factors. One factor is chemical, we can say chemical reaction, and that factor is known as chemical fouling. Or second one is due to, we can say, biological. There may be a biological reactions due to growth of algae in the warm water and deposition of we can say ash particles in the flue gases are some of the forms of foulings. To consider this fouling as a thermal resistance, we know the fouling can be obtained experimentally. By how we can find experimentally? By determining the overall heat transfer coefficient. If we can calculate the overall heat transfer coefficient U, then we can find the fouling factor. There are two conditions. One condition is a dirty condition, second is the clean condition. If U, overall heat transfer coefficient, dirty, dirty, if U dirty, when the heat exchanger is we can say after use, and U clean, U with subscript clean is the overall heat transfer coefficient when the heat exchanger is clean. So we can write down the equation, which is the thermal resistance, which is also known as fouling factor. It will be equal to 1 by U dirty minus 1 by U, we can say, clean. If the surface is fouled by deposit formation on the both sides, then the total thermal resistance in the path of the heat flow between the hot and the cold fluid can also be expressed, and that may be considered by considering two foulings. We will consider the RF will be in the form of two. RF will be in the form of inner side and outer side. It will be RF inner side and RF outer side. I want to conclude again what is fouling and fouling factor. Fouling is a form of scale formation at the surface of the heat exchanger, and the factor which is in the form of resistance due to scale formation due to fouling is known as fouling factor. The reason for the fouling factors are chemical reaction, or there may be a biological reaction, and we can consider the fouling in the form of overall heat transfer coefficient for the clean condition and for the dirty condition. The next topic is the heat exchanger analysis. In our syllabus, heat exchanger analysis of two type. We can analyze the heat exchanger by two methods. One method is a LMTD, which is known as log mean temperature difference method. The next will be NTU method. It is known as number of transfer unit method. We know heat exchangers usually operate for a long period of time without changing their operating condition. Therefore, it is modeled for steady flow. We will consider the flow is steady. And we will also consider the mass flow rate, which is represented by M. Mass flow rate for the fluid, it's going to remain constant. The fluid properties like temperature, velocity, etc. at inlet and outlet remain unchanged. They are also constant. Next is the change in kinetic energy. There are changes in the kinetic energies and potential energy, specific heat and conduction along the length of heat exchanger. We are going to consider they are negligible. Kinetic energy, potential energy, these types of energies at the inlet and outlet, they are negligible. We will consider it. It is an assumption. The outer surface of the tube of the heat exchanger is well insulated and it does not allow the heat transfer to the surrounding. Heat transfer occurs between the hot and the cold fluid only. We can say heat transfer occur only between hot and cold fluid only. Hot and cold fluid only. No fluid. There is one more assumption we are going to consider. We will consider no fluid is undergoing phase change. No phase change. It is also one of the most important assumptions. Now, by the first law of thermodynamics states that the rate of heat transfer from hot fluid be equal to the rate of heat transfer in the cold fluid. Energy lost by the hot fluid will be equal to, let Q by the hot fluids will be equal to Q. Heat transferred, heat lost by the hot fluid will be equal to heat gained by the cold fluid. So what we can say that if the subscript H is for hot fluid and subscript C is for cold fluid, the heat transfer equation, which is also, we also know that mCp delta T, for the hot fluid it will be m dot, which is the rate of mass flow rate of the hot fluid, Cp of the hot fluid, temperature difference of the hot fluid. This is the THI hot fluid inlet temperature, THO hot fluid outlet temperature. This is the amount of heat lost by the hot fluid. We can say heat lost by hot fluid will be equal to heat gained by the cold fluid. This is the heat gained by cold fluid, which is one of the most important assumption for the analysis. Now let us try to understand the first analysis, which is a log mean temperature difference method, or LMTD method or analysis for the heat exchanger. For this case, we are going to consider tube in tube heat exchanger. Means there is a one tube, over that there is another tube, which is a tube in tube type of heat exchanger. For this case, this type of heat exchanger, we can say the temperature distribution will be like this. Suppose again I'm going to draw the tube in tube type of heat exchanger. This is the inner tube through which one fluid is flowing, let's say hot fluid is flowing, and through the outer fluid, let's say another fluid is flowing, which is a cold fluid. We have assumed a parallel flow arrangement for this temperature distribution. For the length, total length, what will be the temperature distribution for this case? For the parallel flow, it will be, we can say, this is the exit, this is the inlet side, this is the outlet side. Hot temperature fluid will be on the upper side and cold fluid temperature distribution is on the lower side. inlet temperature. We can represent this by our temperature distribution. This is the flow of hot fluid from THI to THO, and this is from TCI to TCO for the parallel flow. Now, log mean temperature difference analysis. For log mean temperature difference analysis, the temperature difference between the hot and the cold fluid varies. We know this is the inlet and this is the outlet. From inlet to outlet, there is a change of temperature, change of difference of temperature. It is convenient to deal with the log mean temperature difference. We will not deal with the temperature difference. We will deal with LMTD, which is also represented by delta, or we can say it is also represented delta TLM. These are the symbol. We are not going to do the analysis by temperature difference. We will do the analysis by considering log of that log mean temperature difference, and which is represented by delta TLM. Delta TLM. Consider, let's say, U is the overall heat transfer coefficient. Let's say A is the area, surface area for the heat exchanger, and delta TML with subscript LM is the log mean temperature difference. First of all, we know we can put the value of delta T. Instead of delta T, we will use the delta T LM, which is a log mean temperature difference. The first case is the parallel flow heat exchanger. The first case is the parallel flow heat exchanger. In this case, we know both fluids, hot fluid and the cold fluid, they are moving in the same direction. They are moving in the same direction. As we have already drawn the diagram, for this case, it is the arrangement for the parallel flow heat exchanger. Hot fluid and cold fluid, they are moving in the same direction. The temperature distribution for this arrangement is represented by this diagram. The temperature difference between the hot and the cold fluid is large at the inlet. We know this. At inlet it is large, and it decreases exponentially towards the outlet. From this diagram we can easily observe this. The temperature of the hot fluid decreases and the temperature of the cold fluid increases. There is an increase of the cold fluid temperature, decrease of hot fluid temperature due to exchange of energy. Now apply the energy balance. We can apply the energy balance for differential element. We will consider, first of all, we will consider a differential element. How we can consider the differential element along the length? Let's say at distance x, at distance x from the inlet, consider a differential element. With this differential element, the area of differential element, let it is A, capital A. Now small dA is the area for this differential element, and there will be some change of the temperature for this. Let's say it is delta T. Some amount of small, यहाँ पे some amount of small heat transfer will be there. Let's say it is delta Q, and that delta Q is due to temperature difference, which is, we can say, it will be dTH dTc. Cold fluid temperature increases, its value positive. Hot fluid temperature decreases, its value is negative. On the left hand side, the temperature difference is represented by delta T1. The difference of these two temperatures, THI and TCI, is represented by delta T1. On the right hand side, the temperature difference is represented by delta T2. Some amount of mass of the cold fluid is flowing, let it is mc. At the same time, in the parallel direction, mass of the hot fluid is flowing, having mass, hot fluid mass mh. Now we will apply the energy balance. Energy balance, the rate of heat transfer delta Q is the small rate of heat transfer for the travel x to delta x, for travel x to delta x, from x to delta x, for area dA. The equation will be dQ will be equal to equation will be with minus sign mCp delta T, mass of hot fluid, Cp of hot fluid, temperature change of hot fluid. And for the cold fluid, it is for the hot fluid. At the same time, for the cold fluid, equation will be in the form of mc, cpc and dtc. Hot fluid temperature decreases, its equation is with negative sign. Cold fluid temperature increases, its equation is with positive sign. Now the change of temperature, we know this. For that differential element, the change of temperature delta T, let's say that delta T is Th minus Tc. At this location the temperature is, let's say, Th. At this location, let's say, temperature is Tc. The difference of these two temperature is represented by delta T, Th minus Tc. Now in differential form, this equation will be d delta T. We can write down d Th minus dTc. By solving, when we will solve it, we can say dTh will be minus dTq and divided by mc, mh, cph in the form of cold fluid temperature, del q divided by mc, cpc. When we will put the value of dq and dtc, in this equation, which we have already assumed, the equation will be in the form of del q 1 by mh divided by cph plus 1 by mc, cpc. We also know that at the same time, this del q, the change of heat transfer, exchange of heat transfer from one fluid to another fluid, can also be represented into the form of UA delta T. For differential element, the area is dA, temperature change is delta T, and coefficient is overall heat transfer coefficient. From these equations, from above all these equations, we can find the value of d delta C. d delta Tc, you can find the value of d delta T. d delta T will be minus u delta T dA. Within the bracket, we will put the value of this 1 by mh divided by cph plus 1 by mc cpc. After simplification and rearrangement, we can find the value of after arrangement, we can find the value of a factor, or we can say we can put the value of these two terms into the form of b. The summation of these two terms is represented by b. We will put the equation value of b in this equation, and then we will integrate this equation from inlet to outlet for the heat exchanger. When we do the integration from delta T1 to delta T2 for the above equation, the final equation after rearrangement and simplification, the final equation will be for log mean temperature difference. We are interested to find the equation for LMTD, log mean temperature difference. How we can find the value of log mean temperature difference? By rearrangement and simplification. Finally, we will get the equation. These are the various steps. We will find the value of log of delta T1 divided by delta T2. Then we will find the value of Q. Q is equal to UA divided by this. In this equation, we will simplify the equation for Q. Q will be in the form of UA delta T1 minus delta T2 divided by log of delta T1 divided by delta T2. When we will compare this equation with the Q is equal to UA delta T, this delta T will be the form of temperature difference, which is logarithmic temperature difference, LMTD, and its value is in the form of delta T2 minus delta T1 log of delta T2 by delta T1. This temperature difference will be used instead of delta T. Instead of delta T, we will use this new temperature difference, which is a log mean temperature difference, which is suitable for temperature difference in tubular heat exchanger, where delta T1 and delta T2 represents the temperature difference between hot and the cold fluid at the ends, inlet and outlet. It makes no difference which end of the heat exchanger is designed.